You know, there's this invisible magic that makes our entire modern world tick. It's the unsung hero that keeps your texts, your videos, and your calls from turning into a garbled mess. We're talking about channel coding, and it's the secret sauce in your Wi-Fi, your 5G, pretty much everything wireless.
I mean, really think about it for a second. You could be walking through a crowded city, streaming music with buildings and cars all around you, and somehow your signal just works. How is that even possible? The airwaves are basically an invisible storm of noise and interference. And this is the huge problem that engineers had to solve. Wireless communication is, by its very nature, incredibly fragile.
So to really get why the solution is so brilliant, we have to first respect the problem. The wireless channel, the air between your phone and the cell tower, it's not empty space. It's a really hostile environment. Your signal is bouncing off buildings, getting absorbed by trees, and crashing into other signals. All this chaos creates something called fading, where the signal strength can just plummet, sometimes disappearing completely for a split second.
Okay, now this is the real villain of our story today. See, fading doesn't just cause a little bit of random static. It's much, much worse than that. When your signal hits one of those deep fades, it doesn't just mess up one little bit of data. Nope. It completely wipes out a whole chunk of bits all in a row. We call this a burst error. And for data, it's an absolute nightmare.
Just look at this. A single fading event, maybe lasting just a microsecond, has totally corrupted 4 bits one after the other. Now, a simple error-fixing plan that's designed to catch maybe one stray error here or there, it would be completely overwhelmed by this. It would look at this chunk of data and just throw its hands up. There's no obvious way to figure out what the original message was supposed to be. This right here is the fundamental challenge of going wireless.
So how in the world do you fight back against an environment this chaotic? Well, you don't fight harder, you fight smarter. You actually plan for the errors before they even happen, and you build a defense system right into the data itself. And that technique is called channel coding.
Channel coding is all about adding extra, helpful information to our original message. But, and this is important, it's not just about, sending 3 copies of everything and hoping one makes it. That'd be super slow and inefficient. Instead, it's about adding these mathematically clever, structured little bits of extra info. These extra bits, they're called parity bits, and they act like a sophisticated blueprint that lets the receiver rebuild the original data, even if some of it got smashed up along the way.
The whole process is really proactive. It all starts at the transmitter. Before a single bit even gets sent out, an encoder adds that smart redundancy. Then it's transmitted. On the other end, the receiver's first job is to just detect if any errors happened at all. And if they did, it then uses that extra blueprint information to correct them, and hopefully get the original data back perfectly. So you see, we aren't just reacting to errors, we're expecting them, we're planning for them from the very start.
Now, as you can probably guess, there isn't just one single way to add this redundancy. Engineers have come up with a whole toolbox full of different coding methods, and each one has its own philosophy, its own strengths and weaknesses. So today, let's look at the 2 big foundational types of codes that pretty much everything we use today is built on: block codes and convolutional codes. So on one hand, you've got block codes. The best way to think about these is that they process data one fixed size chunk or block at a time. Each block is its own little world. It gets encoded completely independently, with no memory of the block that came before it. Then on the other hand, you have convolutional codes. These are totally different. They work on data as a continuous flowing stream. And their key feature is memory. The way any given bit gets encoded depends not just on that bit, but also on the bits that came right before it. This creates this powerful chain of dependency that can make the code incredibly robust.
Okay, so we have these 2 really powerful tools in our toolbox, right? Block codes, which are mathematically neat, and convolutional codes, with that awesome memory feature. And they both work great on channels where errors are kind of random and scattered. But here's the million-dollar question. What happens when we put them up against our main villain, the burst error? Well, the tough truth is, even these amazing codes can get totally crushed. A long burst of errors can just overwhelm a block code's ability to fix things. And for a convolutional code, it can get so confused that it just completely loses its way. Believe it or not, in a really bad fading channel, using one of these standard codes can actually make things worse than sending no code at all.
So if the codes themselves aren't quite enough to do the job, what are we missing? There's got to be a missing piece to the puzzle. We need some kind of special technique, a clever trick that specifically targets the bursty nature of wireless errors and changes them into something that our codes can handle. This is what I like to call the wireless special sauce.
And that secret weapon is a brilliant little idea called interleaving. Now, the concept itself is beautifully simple, but its impact is just massive. Interleaving doesn't add any new data. It doesn't change the code we're using. All it does is shuffle the order of the coded bits before we transmit them, but it does it in a very specific, very structured way.
Okay, stick with me, because this part is really cool. Imagine we take our coded data and we write it into a grid or a table, filling it up row by row. But, and here's the genius trick, we don't transmit it row by row. We read the data out and transmit it column by column. Now, when one of those nasty burst errors strikes, it hits a consecutive chunk of this column-based data. Then, at the receiver, we just do the exact opposite. We write the incoming data back into a grid, filling it up column by column, and then we read it out row by row, just like it was originally.
So, what did all that shuffling actually accomplish? Well, look! That single, massive, destructive burst error that happened out in the airwaves has now been scattered. It's spread out across multiple different code words. So instead of one code word having 4 errors and being totally unfixable, now maybe 4 different code words each have just one single error. And here is the punchline. Interleaving transforms an unbeatable enemy, the burst error, into a much more manageable problem. Just a few scattered single-bit errors. And those are exactly the kind of errors that our block and convolutional codes were born to fix. It's brilliant.
This amazing combination, powerful channel codes plus the clever trick of interleaving, that really is the bedrock of all reliable wireless communication. But of course, technology never stands still. In the years since these ideas were born, engineers have built on them to create codes that are almost unbelievably powerful, pushing performance right up to the absolute theoretical limits of what's even possible. Two of the heavyweights in the modern era are turbo codes and LDPC codes. They both get their incredible power from something called iterative decoding. The best analogy is to think of it like 2 detectives working on a tough case. The first detective makes their best guess, then passes their clues over to the second one. The second detective uses those clues to refine the guess and then passes new clues back. They go back and forth like this, and with each pass, they get closer and closer to the right answer. This clever process lets these codes get remarkably close to the ultimate speed limit of communication, what's known as the Shannon limit, and it's what powers everything from your 5G phone to the deep space probe sending pictures back from Jupiter.
All right, so let's just quickly wrap up what we've learned. The airwaves are a tough place for data, and that fading phenomenon causes errors to clump together in these destructive bursts. To fight this, we use channel coding to add smart, structured redundancy. But the real magic, the secret sauce for wireless, is interleaving, that shuffling process that breaks up the error bursts. This powerful 1-2 punch of coding plus interleaving is what makes our wireless world actually work. It's the invisible mathematical engine that makes sure your video calls don't drop, your music streams clearly, and your texts actually get there.
So the next time you pull out your phone and just seamlessly connect to this whole world of information, hopefully you'll have a new appreciation for the incredible, mind-bending ingenuity that's happening behind the scenes. Knowing how the magic trick works doesn't take away the wonder. If anything, I think it makes it even more amazing.
Hey, if you enjoyed this deep dive into the world of wireless communication, please make sure you subscribe to the channel and give this video a like. It honestly really helps us out a lot. And if you have any questions, or if there's another complex topic you'd like us to break down for you, please let us know down in the comments below. Thanks so much for watching.